Good morning, good afternoon, good evening, wherever you are. In this talk, we'll be focused on understanding the performance of machine learning in mobile smartphones. Specifically, we'll be focused on understanding the end-to-end performance of machine learning in smartphones. My name is Vijay Janaparidi, and I'm a faculty member at Harvard, and I'm filling in for my student Michael Bush. This is work done in collaboration with my colleagues Zara Azad and Professor Joshi at Boston University. Let's get started by looking at what's happening in the broad ecosystem of mobile smartphones. Long gone are the days when you and I would simply search the web or watch a video. Increasingly, we're witnessing applications that are using machine learning in real time to provide enhanced user experience. Some of the tasks include image classification, detection, segmentation, augmentation, and so forth. A lot of these capabilities are really being enabled by what's underneath the hood. In particular, I'm referring to the ML hardware, be it in the form of vector ISA extensions in CPUs, or mixed precision support in mobile GPUs, or even customized NPUs that are designed to accelerate neural networks. There's a wide range of hardware that is coming about as we go into the future. And as a result of this, there is a growing demand to benchmark the performance of AI systems. In the context of mobile, there are industry standard benchmarks such as MLPerf and AI benchmark that provide a wide suite of different kinds of workloads in order to assess the capability of the hardware. They focus on a wide variety of different tasks such as classification, detection, segmentation, language processing, and so forth. But the end goal for all of these benchmarks is to assess the performance of the handsets in order to inform end users and consumers. But this leaves me with the extremely critical question. Are these benchmarks truly representative of end users' experience? Well, let's take a real-world application and try and understand what's going on underneath the hood in order to have a deeper appreciation for the complexity involved here. In this particular video, for instance, we're seeing that smartphones actually processing the images coming in from the sensor in real time and overlaying boxes onto the image based on what the neural network output is. Let's try and understand this in a more systematic fashion from the data capture all the way to the inference. The first step is for the camera to actually do the data capture and to dump the data into frame buffers, which are processed by the ISP. After that data is available to the application, there's a pre-processing step where the neural network pipeline actually has to take the large images and then try and do processing on them at much lower resolutions. If you look at a typical camera, for instance, it might have something like a 12 megapixel resolution, but you don't necessarily want to work on a 12 megapixel image because that can really slow the application user experience down. So therefore, it's very common and typical to downscale the image down to something like 240 by 240 or 300 by 300. And that's one of the first things that the neural networks do. The next thing that has to happen is invoke the neural network framework. For example, NN API is a very common framework that's widely available on Android devices. It is a vendor-neutral platform, but there are also vendor-specific platforms, for example, like Snappy, which is provided by Qualcomm for their chipsets that is designed specifically to accelerate neural networks. The job of the framework is to exercise the hardware underneath the hood, be it on the CPU, the GPU, the DSP, the NPU, or some combination of all of them. After the graph is executed, the remaining part of the pipeline is to do the post-processing. This is highly dependent on the task being performed. For instance, classification tasks don't really have much post-processing to be done outside of simply computing the softmax probabilities. However, in other applications such as PostNet, for instance, there's a fair bit of post-processing that actually has to happen. Now, if you look at existing benchmarks, by and large, they focus primarily on the framework and execution. They don't actually look at the end-to-end pipeline, which is what really determines end-user experience. So, what we want to do is try and understand the performance from the overall big picture, from the perspective of execution of the model, as well as the perspective of all the overheads that are associated in order to support the model's capabilities. In other words, what are the overheads that are associated with the algorithms, frameworks, and hardware? For example, in algorithms, there's overhead associated with data capture, pre-processing, post-processing. For frameworks, there's a lot of driver code that needs to run that actually needs to do very intelligent scheduling to make the most of the silicon. Finally, you have the hardware offloading costs themselves. These are just a sampling of the different kinds of tasks that we have in a mobile SoC. So the goals of our study are to perform an end-to-end analysis of AI tasks, using both benchmarks and Android ML applications, And we want to understand how the individual stages of the ML execution pipeline influence the quality of experience for application performance. Finally, we want to be able to quantify that AI attacks in real-world systems. All that said, before I dive into the details, allow me to introduce the experimental setup. Our main evaluation platform is a Google Pixel 3 device, which has a Snapdragon 845 chipset. We have evaluated the same set of experiments on many different chipsets, and the conclusions remain the same, be it whether it's a Qualcomm chipset or a Samsung or a MediaTek device. The next thing is that we consider different evaluation frameworks, like the NNAPI framework from Google, the TF Lite framework from Google, and the Snappy backend from Qualcomm that is designed to make the most of Qualcomm chipsets. Then we look at a wide variety of machine learning models that are typical on mobile devices for tasks such as image classification all the way out to segmentation, detection, and so forth. Our goal is to measure the execution stages both in benchmarking utilities and real-world Android applications to determine what the end-to-end performance delta looks like between them. For starters, we're going to focus on the algorithmic side. In general, we're going to be looking at latency, and we're going to be looking at that latency across a wide range of different neural network models. In this particular graph, I'm comparing the performance of benchmarks against the performance of applications that are using these neural networks inside to provide a useful feature. The first thing we want to do is ask this question of how does performance compare when we're running ML benchmarks versus running a real end-user mobile application. You will notice across all of these benchmarks here and across all of these apps, there's a delta. And this delta is consistent in the sense that the app is always taking longer to execute than the benchmark models themselves. There are many reasons for this. By and large, it turns out every app has generally more computational requirements and more system requirements. The apps are also doing a lot of pre-processing and post-processing as compared to what the benchmark utilities do. We'll be digging into this a bit more further soon. But the key nugget is that across all of these scenarios that we look at here, it's up to 50% difference in the latency per inference when we're doing the inference on the CPU across the app versus the benchmark utility. Now let's try and understand where this delta is really stemming from. What we see is that there's data capture and there's pre-processing. Both of these play a very critical role. In Android applications, pre-processing and data capture is something that happens as part of the real-time pipeline. So for example, if we were to look at EfficientNet, and we look at this particular bar here, which corresponds to the application, we see that the pre-processing plus the data capture is almost equivalent to the actual inference latency. If we look at the benchmark, which is on the left-hand side, we see that there's only data capture and there's really no pre-processing. This is because the pre-processing is effectively already done. The data is already scaled down. So typically when you're looking at this data, the data set's ready and you're simply ingesting that data into the network and then running it through the framework. So therefore, you don't see any pre-processing overheads. So the first of the takeaways is that data capture and pre-processing are actually quite critical. They are quite as critical as the inference itself. And second, there's clearly a difference in terms of the characteristics of how the benchmarks perform and how the application actually performs. Now, if we look at the bottom chart, this is effectively taking the data that's up on the top and breaking it down one level into more detail by showing the relative overhead of data capture and pre-processing with respect to the inference latency. In general, what we see is that in scenarios such as MobileNet or EfficientNet, the data processing or the data capture and the pre-processing are almost equal to each other. And that is substantial as compared to what's actually happening in the benchmarks, where there's really nothing going on in terms of the benchmarks. So this means that we have to be very conscious about the non-model parts of the execution time. And therefore, it is extremely important to capture them. Next, let's move on to see another side of AI attacks, which is in terms of the frameworks. Specifically, we want to understand how, given a framework is set up, how can the performance change? We're going to look at where performance can degrade. We're going to look at a case study where we're running EfficientNet Lite using NNAPI on a Pixel 3 device. What we observe is a 7x slowdown in latency per inference when we're running it through NNAPI. even when we ask the NN API to actually use the hexagon DSP, which is designed to be able to run the network very efficiently. Let me show you the chart and explain what's going on behind the scenes. On the y-axis, we're looking at latency per inference, and the x-axis, we're looking at different ways to execute the network. So here we're seeing what happens when the T of light engine is using the hexagon delegate backend. We see that inference is remarkably fast. We're comparing this against with T of light doing the inference with CPU 4 threads and CPU 1 thread. Both these cases, we see that the inference is still much better than NN API. Now, NN API is a completely different framework. And even though it's supposed to be vendor neutral and supposed to support all different ops, it does not quite support the efficient net efficiently. Now, this is not a cherry-picked example. There are many other scenarios where you see this sort of behavior. And the key reason is that a certain op in the neural network is actually not supported, and therefore the NN API has to fall back onto the CPU. But because it keeps trying to schedule the work to the hexagon DSP, and the work ends up bouncing between the DSP and the CPU, you end up with a very large slowdown due to the back and forth inefficiencies. Let's go one step further into the details. We're going to walk through 4 different scenarios here. 1, 2, 3, 4. In the first scenario, I only want to use the CPU, so you can see that the CPU utilization is remarkably high. That means everything is working as expected. In the second scenario, I want to use the DSP, the compute DSP. So you can see that the DSP starts up and it stays floored and executes really well. In the third scenario, I actually want to use the NN API and schedule it to the DSP. And you see that the DSP utilization goes up, but very quickly it falls back and stays low, remarkably low. What's actually happening is that because a certain operator is not well supported by NN API on the DSP, there's a lot of back and forth happening between the CPUs and the DSP. You can tell this by the fact that the CPU activity actually goes up. And it also turns out that there are a large number of context switches that are happening here. And that is indicating to us that the workload is actually trashing not only between the CPU and the DSP, but it's also trashing across the different cores. Therefore, you end up with very severe degradation in terms of performance. Finally, I also want to touch on the notion of what ends up happening when we're running networks the very first time versus after the hardware has been actually primed up. So what we're looking at is latency on the y-axis and how the latency changes as we kick off multiple inferences. The very first time we run it, where we're offloading something to the accelerator, we see that we get a massive penalty. However, after that, this overhead is quickly amortized and the predominant latency portion is just the inference and not the offloading overhead. During the initial offload, the overhead ends up being big because the operating system has to do a lot of setup and get the accelerator actually ready. So this means that the accelerator needs to be primed before executing it. Now, in the context of benchmarks, these kinds of behaviors are actually not measured. However, in real-world applications, you are not going to keep the IP primed up at all times because that's inefficient from a power consumption sort of perspective. So these kinds of cold starts can actually be quite critical for user experience. And so we see that offloading is actually quite important to keep in mind. And we are actually looking at this data when we're running Snappy, which is an optimized tool chain for the Qualcomm backend. And yet we find that these kinds of differences actually exist. This basically implies that we need to be able to understand what the performance characteristics look like when we're using different frameworks at different times. Last but not least, I want to quickly touch on the notion of multi-tenancy, where the goal is to actually support the execution of multiple processes at the same time, effectively contending for workloads. And we want to make sure our latencies don't actually increase. What this graph is showing is how latency is changing as we are scheduling more processes through NN API. Specifically, we're scheduling multiple models, one through NN API to the DSP, and the rest fall onto the CPU. So as we can see that when we schedule more processes, the latency starts going up. Specifically, we see that the latency starts going up for data capture and pre-processing because these portions are actually run on the CPU, not on the hardware accelerated engine. And therefore, for inference, we don't see any impact on latency from an NN API standpoint. However, the other sources of overhead start dominating. Finally, when we're also scheduling multiple models that end up contending for the acceleration, in other words, we want to run 1, 2, 3, 4, 5, 6, 7, 8 models all on the exact hardware accelerator instead of leveraging the rest of the components in the SoC, we see that the overhead starts dominating quite a bit, implying that in the future we have to be careful about how we actually schedule tasks. In effect, what this AI tax is telling us is there are several sources of overhead that we have to be careful of when we're measuring the end-to-end performance of AI applications. So in summary, there are many different SoCs, frameworks, and benchmark utilities out there in order to measure performance. However, it is important to measure the end-to-end performance and not just the model performance. Moreover, there is a real need for deeper introspection tools that allow us to gain insights as to what's actually going on underneath the hood. And with that said, I encourage you to see the paper for additional details.